Recently in class we've been looking at patterns, sequences, and series. So we're going to continue that today by looking at the sum of odd numbers. So let's add up odd numbers and see what happens. Well, if we just take our first odd number, we have 1, so by itself, that equals 1. If we add up the first two odd numbers, 1 plus 3, we get 4. And let's continue this. I want you to do this on your own, look for a pattern. So what happens if you add up the first 3, the first 4, and the first 5? So add those up, pause it, think about it, and come back when you see the pattern. Okay, so here we get 9, 16, and 25. So hopefully you notice that those sums are all perfect squares. Now what's interesting is that this is the first problem, the second series, the third series, the fourth series, and the fifth series. So if you look at which series in line it is, the second series here, the sum is 4. The third series, the sum is 9. The fifth series is 25. So what would happen if we went all the way down to the nth series? What would you expect the sum to be? Well, following the pattern, it should equal n squared. Well, the other part of this becomes, how would we write this stuff on the left side here? Well, I know that we are adding up 1 plus 3 plus 5, but where would you stop for the nth series? So even though we've identified the formula for the sum here, 1, 4, 9, 16, 25, n squared, we also need to figure out a way to determine the nth term. So let's look for another pattern here. Looking at the last number in each series, the first number is 1, the second is 3, the third is 5, the fourth is 7, the fifth is 9. So these numbers here form an arithmetic sequence, and they're increasing by 2 each time, so the common difference is 2. If we were to back up 1, the term before this would be -1. So the nth term in this sequence here would be 2n minus 1. So if you start adding at 1 and add all the way up to 2n minus 1, the sum will be n squared. So this formula seems to work for our first 5 odd numbers. So the sum of the first 2, the sum of the first 3, the sum of the first 4, the sum of the first 5. And we could keep doing this and keep adding to check this formula. But even if it works for the first 100 odd numbers, that does not guarantee the formula will always work. Even if you keep checking and it works all the way up to the first 1,000 odd numbers, that still does not guarantee that the formula will always work. So we need a different way to be able to prove that this formula is always going to be true, no matter how many odd numbers you want to add up. So that process is called mathematical induction, but before we get there, I have a couple other things that I would like you to think about. So first, think about dominoes. Now, I know that this is a silly image. I wish I had actual pictures of dominoes here for you, but picture them in your head. Remember playing when you were little, where you would line them all up and you would make some crazy pattern, knock over the first one, and they all fall over? Well, what would you have to do when you're setting up your dominoes to make sure that that actually happened? And we could see here I have my 4 dominoes, so if I was to push the first one, the rest of them will get knocked over. But notice, in order to start the process, I had to knock over that first domino. If I just sit here and stare at it forever, nothing's going to happen. But the other thing is, if I want these to all knock over, I better line them up correctly in the first place to begin with. If I took two of the dominoes and pushed them over here, then I could still come, knock over my first domino, this one would fall over, but nothing's happening here. So these dominoes stay standing. Okay, we're going to use this picture of dominoes to explain mathematical induction. We have to make sure that our formula here works for the very first number. What if I just look up here? If I plug in a 1, is the formula going to work on both sides? And if that's true, the second thing we have to do is make sure that the dominoes are spaced out correctly, so that every time I knock a domino down, the next one also falls over. So that's where the proof gets a little tricky, something new that you haven't seen before. So again, before we get to the actual problem, I have a smaller picture for you. When we add up the first 4 odd numbers, it equals 16. So this is something that we know is true. Now, according to our formula, if we go to the 5th series, 1 plus 3 plus 5 plus 7 plus 9, according to the formula, that should equal 25. But does it really? Well, what induction does is it uses something that we know is true in order to prove the next thing in line. So using numbers, here's what our problem's going to look like. If I want to add up 1 plus 3 plus 5 plus 7 plus 9, I already know that 1 to 7 adds up to 16. So I could say, well, this is 16, and then I'm adding 9 more in. What's 16 plus 9? 25. Okay, so 1 plus 3 plus 5 plus 7 plus 9 does equal 25. Is that what the formula says it equals? Yes, it is. So things seem to be on the right track. Okay, you're like, teacher, I already could add up 1 through 9 and I know it's 25. What the heck did you just do? Well, we need to do this process, but instead of using the first 4 and then using it to figure out if the 5th one works, we're going to have to throw some variables in here. So here we go. Back to where we started. We are going to try to prove that this formula here is true no matter what. The way we're going to do that is first by showing it works for 1. Otherwise, there's no point in even checking it. Then, what we need to do is make sure our dominoes are spaced out correctly. In other words, make sure that if I could knock 1 domino over, that the next one in line is also going to work. So make sure that you copy this part of the problem down word for word. There's a definite structure to these types of problems that I expect to see from you all of the time. So we start by saying, consider the statement 1 plus 3 plus 5 plus 7 plus ... plus 2n minus 1 equals n squared. Our first step is going to be called the anchor step. And we need to show our statement is true for n equals 1. Or in other words, if I look at the first term of the series and I plug in 1 on the right side, are they going to match? So what we're going to do is we're going to use our formula here for our sequence. We're going to plug in a 1 for the n. We're going to plug in a 1 for n here. So we have 2 times 1 minus 1 equals 1 squared. So on the left side, that's 1. On the right side, that is 1. 1 does equal 1, so this is true. We just knocked over our first domino. Next comes the induction hypothesis. Now in science, you have the scientific method. If you're going to run an experiment, you make a hypothesis, and that is something that you are assuming is true, and you want to set up an experiment to see if it really is or not. So similar idea here. We are going to assume our statement is true for n equals k. So what this means is we're picking out some number k where we say the formula works for this number. That's like going to a huge line of dominoes, stopping somewhere in the middle and saying, I know I can knock this certain domino over. So what we do is we go back to our original formula and we replace all of the n's with k's. So 1 plus 3 plus 5 plus 7 plus dot 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 plus 2k minus 1 equals k squared. So now for us, for the rest of this problem, this is something that we are assuming is true, and we get to use it as if it was true. Next is the induction step, where you say, what about n equals k plus 1? So remember, in our hypothesis, we found a certain domino, k, and we assumed we could knock it over. So now I'm looking at that next domino in line, k plus 1. Whatever comes right after that one, will that also be true? So we go to our original formula, and every place you see an n, we replace it with k plus 1. So now we have this. Just a couple math things. Whenever you substitute in k plus 1, make sure that you put parentheses around it. And also here, since our k plus 1 is in parentheses, those old parentheses turned into brackets. Okay, so where are we at? Now we have to somehow show that since our induction hypothesis is true, what we've written here in our induction step is also true. Now in order to have this work out nicely, I'm actually going to rewrite this question I just wrote by moving this last part of it over a bit. Just making a little bit more space. So remember that these dot dot dots here just show that we're skipping a bunch of the numbers in the sequence. For example, right here, I know that if I was to move those dot dot dots over, the next thing after the 7 would be the 9. We just don't write it because we're not sure how long the series is going to go on. Now the same thing on this side. There has to be some number that comes right before 2k plus 1 minus 1. We just don't show it. So I want to peel back that curtain and look to see what comes right before. This piece here is the k plus first term in the sequence, and I found it by plugging k plus 1 up here in our original formula. So to figure out the term right before it, well, if this is the k plus first term, the one right before it would be the kth term. So to figure out this one, we plugged in k plus 1. To figure out the one right before it, you plug in k, again up into that 2n minus 1 from our original formula. So the term right before would have to be 2k minus 1. So I suggest that you always write this piece in during the induction step. It is going to save you some heartache later on. So now that we've set everything up, we need to actually get into the algebra part of our proof, where we are actually going to show that what we have here on the left really does equal what we have on the right. Now if I was just doing this on paper, I would continue to write. Because I'm working with slides, I'm about to go to a new slide. So because it is a proof, we need to, again, start with what we have on the left. So I'm going to rewrite this first and then work my way through and hopefully end up here. So first we write the left side of the problem. I want to know what this equals. So what's interesting here is I'm saying I'm starting adding at 1 all the way up until 2k minus 1 and then plus that next term in line. So if you look at this part of the problem, from the 1 all the way up to 2k minus 1, that should look familiar. That is exactly what we have written in our induction hypothesis. So our hypothesis was that if you start at 1 and add everything up to 2k minus 1, that would equal k squared. Well, so we could use that in our problem. Starting with 1, everything up to 2k minus 1, all of that adds up to k squared. And then we have our next piece, so plus 2k plus 1 minus 1. Now we know that this is true by the induction hypothesis. So I want you to write this so you're giving me your reasoning for the substitution that we made. Now we need to use algebra to simplify. So this equals k squared plus 2k plus 2 minus 1, which is k squared plus 2k plus 1. We have a trinomial, so let's factor it. This is k plus 1 times k plus 1, and those are identical, so I could write that as k plus 1 squared. Now take a look at your induction step. What we were able to do is show that the left side matches the right side. I started with my left here. All I did was use algebra and my induction hypothesis to simplify it and end up with the right side. So we have shown that if I could knock over the domino that is k in line, the next one after it, the k plus first domino, also knocks over. And we were able to knock over the first domino. So we've guaranteed now that since the first one could knock over, the second one knocks over, which knocks over the third, the fourth, the fifth, and all the way down the line for every single positive integer. So without having to go through and actually check this for every single number, we have a valid proof that this formula works. So you want to finish it up with a conclusion. Therefore, it is true for n equals k plus 1, and it is true for all n, so 1 plus 3 plus 5 plus 7 plus ... plus 2n minus 1 equals n squared. And then we are done with our proof. So let's look over it again just to remember what happened, put it all together. We started off with the formula we wanted to prove here. And so we did our anchor step, where we made sure that it was true for n equals 1, or the formula at least works for the first number. Then we said, let's pick a random number k and assume that the formula works for that number. Next, we need to look at the number right after it, k plus 1. Does the formula work for that one as well? So in order to do that, we started with the left side here, and we had to simplify it. In our first step, we used the induction hypothesis to replace all of this with k squared. And then we combined the two, got our like terms together, and factored, and saw that it equaled what the formula said it was going to. So our first domino knocked over, the rest of them are spaced out in a way that they will knock each other over, and our proof is done. That's mathematical induction. One final thought before I let you go. Grammar is important here. Like I said, this is the structure that all of your induction proofs should follow. So take out a highlighter and highlight these words. Consider the statement. Anchor step, show our statement is true for n equals 1. This is true. Induction hypothesis, assume our statement is true for n equals k. Induction step, what about n equals k plus 1? Does, question mark, by the induction hypothesis, therefore it is true for n equals k plus 1, and it is true for all n, so. All of those words that we just highlighted, I need you to write them for every single induction problem that we do. You do need to memorize it, you need to be able to do that every single time. It gives you the structure of how to set up the problem, and then just based on the exact problem we're doing, the math within might be different, but the structure will always be the same. Now go ahead, try out the homework, and make sure that if you have questions, you find a friend that you can ask or come and see me if there's anything that is still not clear.